Let's take a look at SLO 15 and 16. This is part 2, and we're going to be continuing off where we left off with the law of sines. But again, the goals of this video are to be able to determine the number of different oblique triangles that exist given certain side lengths and angle measures, as well as use the law of sines and the law of cosines to solve oblique triangles. We will be determining all missing side lengths and angle measures. But let's continue back at the law of sines involving SSA triangles. Let's talk about the law of sines involving SSA triangles. So this is where a lot of the ambiguous cases come from, and it's mainly because when you use the law of sines, there are possibilities of what angle you're given. Consider the fact that the angle of sine is positive in both the first and second quadrants, meaning you essentially could have two angles, and that could create a number of different triangles. So there are 4 possibilities of what could happen. There could be no triangle based on what numbers you're given. This is when A is less than H. You could have only one triangle where A is greater than or equal to side length B. You could have 2 triangles where A is greater than H and A is less than B. Or you can have a right triangle where A is equal to H. Let's get into actually using the law of sines with an SSA triangle though. We are given an SSA triangle. We're asked to find side K and round to 2 decimals. So if we first take a look at this, we'll notice that K does not have a value associated with it, not side K, not angle K, meaning we're going to first have to find something that has a side length, and this is N. N corresponds to here, and it doesn't have an angle, but we can find it using the law of sines as our first step. So we'll have the sine of 30 degrees over 9 is equal to the sine of N over 12. Cross multiply here. 12 sine of 30 degrees equals 9 sine of N. Let's simplify this part right here. So the sine of 30 degrees is 1/2, and we're going to multiply that by 12 to get 6. We'll divide both sides by 9. 6/9 simplifies to 2/3, and we're going to set that equal to the sine of N. If we take the inverse sine of both sides, we're able to isolate N. So the inverse sine of 2/3 rounded to 2 decimals is 41.81. So we can now add that to our triangle. So we don't know yet if there are 1 or 2 triangles, but we know that there's at least one. There's not 0 triangles because we have the ability to create that here. So we still don't know the side K. However, if we subtract 30 plus 41.81 degrees from 180, we can now find angle K, 108.19 degrees. So since we know angle K, we can now put this into the law of sines. So we have the sine of 30 degrees over 9 is equal to the sine of 108.19 degrees over K. So I'm labeling this as K1 because there's a possibility for a second triangle, which we'll get into in a bit. But until then, we're going to cross multiply. So K times sine of 30 degrees equals 9 sine of 108.19 degrees. The sine of 30 again is 1/2. And if you put this into a calculator, you'll get 8.55. Divide both sides by 1/2, and you get side length K to equal 17.1. This is only one possibility though. So since side-side angle triangles are considered ambiguous, there is a chance for a second triangle. But this is our first triangle here with all the side lengths and everything figured out. But let's look at the possibility of a second triangle. So we know there's a second triangle because if we took our original angle N, which was 41.81 degrees, and we subtract that from 180, we could also have angle N be 138.19 degrees. So now this shows there's a possibility of a second triangle because when you add 30 to 138.19 degrees, which is our new value of angle N, we still have some degrees left over to create 180 total degrees in the triangle. However, if you subtracted a value from 180 degrees and it does not leave enough room over to create a third angle, you know that there is not another triangle available. So in those cases, there will be one triangle and one triangle only. But in this case, we have two triangles for this ambiguous case. So I'm just calling this angle K2 because it's different than the other triangle. But in order to find the angle of K, we'll do 180 degrees minus 30 plus 138.19 degrees, and that gives us 11.81 degrees. We'll put this into our law of sines. Again, we can use sine of 30 degrees over 9, and then we'll set the sine of 11.81 degrees over K2, since we're looking for the length of side K. So we're going to cross multiply this. Again, the sine of 30 degrees is 1/2, so K times 1/2 is equal to 9 times the sine of 11.81 degrees. That simplifies to 1.84. Divide both sides by 1/2, and you'll get the side length K is about 3.68 if we round to 2 decimal points. Again, this is considered an ambiguous case because you don't exactly know how many triangles there are that are possible, and that's why you have to check. You have to check by subtracting the first angle you find from 180 to see if there is another angle that would work in the triangle. And this is because, again, sine is positive in the first two quadrants, meaning that reference triangles are possible. There is another angle that works with the triangle. So that makes it a little different. This will be the end of part 2 for SLO 15 and 16. We still have to cover the law of cosines, and I will do that in part 3 for this video. So thank you for watching, and continue on to part 3 of SLO 15 and 16.